Hi, this is Mrs. Kinman, and in this video, we are going to be exploring polygons and their relationship between their sides, their angles, and the sum of their interior angles. So what we're going to do is start by looking at some really common polygons and then move on to some less common. Now, this video is not going to go through all the polygons, and it's not actually even going to go through all the ones that I have listed on this slide. What it is it's intended to be a beginning to kind of a discovery lesson that really pushes you to look into more so what is the relationship between polygons and how could we figure out what the sum of the interior angles are of any polygon regardless of the number of sides. How could we do that? And so this is just a beginning to kind of give you a hint on what you can do, and then you can continue exploring this on your own. So let's take a look at some of these common polygons that we see. So the first one we have here is a triangle. So a triangle has 3 sides and it has 3 angles. Now, we want to look at the sum of those interior angles. Well, I've proven before, and so I know you can either prove it yourself, watch my video, or assume it, that the sum of the interior angles of a triangle actually add up to 180. And we can use parallel lines to actually figure that out. Now, this last column here that I'm going to fill out is the measurement of one interior angle of a regular triangle, or a regular 3-sided polygon. And in this case, that's going to be 60 degrees. The reason why is when it's regular, that means that all the sides and all the angles are the same. And so if all of our interior angles are the same, that means they all add up to 60 degrees. Okay, so let's take a look at a quadrilateral. Now, a quadrilateral has 4 sides, 4 angles. Now, the sum of its interior angles actually is going to be 360 degrees. Now, I know that because I know that with this square here, that all of the corners are 90 degrees. Now, be aware that that is not the case with every quadrilateral, but it is the case that they all have a sum of interior angles of 360 degrees. Now, why is that? We might be wondering. Well, a big reason why is if I divided this quadrilateral into 2 triangles, notice what happens here. I've got one triangle whose degrees add up to 180, and I've got another triangle whose degrees add up to 180, and that includes all of my angles only once. So if I have all those angles included only once, 180 times 2 is 360. Now, that 360, we actually have 4 unique angles in here. So in a regular polygon, one angle is going to be 360 divided by 4, which is 90 degrees. Fantastic. Okay, let's take a look at a pentagon now. Now, I know that that has 5 sides, and I can count that it has 5 angles. But what is the sum of its interior angles? Well, I don't know that off the top of my head. So what I'm going to do, just like we did with that quadrilateral, is actually divide it up into triangles. So I'm going to go from this point to some of the opposite points there. Now, notice how we created 3 triangles, none of which overlap with one another. It's really important when you're doing this discovery that we create triangles that don't overlap. Okay, and we want to make the biggest possible triangles. So we don't want to cut it up into a bunch of small triangles that we then have to subtract pieces out of. So as we create this, what we've noticed that we have here is we've created 3 big triangles. Now, what's the sum of this triangle? Well, that's going to be 180. And the sum of the angles of this one is going to be 180. And the sum of the angles of this one is going to be 180. Now, all of these are included in some piece of an angle here. So we don't have to subtract anything out. So really what we can do here is we can just take 3 times 180, and that's going to end up giving us 540 degrees. Now, before, to figure out the interior angle of one of them, what we did is we took that degree, so that 360 divided by 4, and we got 90. So I'm going to do the same thing here. If I take 540 and divide it by 5, I'm going to get 108 degrees. And so that, not 180, oof, that's not right. 108 degrees. So that 108 degrees is going to be what one of these interior angles are. Now, does that seem to make sense? If we kind of erase these lines here, you can see that this looks like it's greater than 90 degrees. Now, it's not fully 180, but it is bigger than 90. So we can do the same thing again, looking at our hexagon. So this has 6 sides, this has 6 angles. Well, let's divide this one up into some triangles here. So I can divide this up into a few triangles. I've got that triangle, that triangle. Ooh, this one's hard to divide into a triangle. What if I go this triangle, this, and this? Now we've got 6 small triangles and we have to subtract out this middle piece. How else could we do this? Well, one thing we can think of is maybe do this and this and this. So notice here how we just created some triangles. With these triangles, you can see that what we ended up getting was we had 4 triangles, and none of them overlap because we took these end triangles and then split our middle rectangle in 2. Then we know the interior angles of a rectangle equal 360, and the interior of these triangles will also add up. So let's take a look, and as we have that, we've divided it into 4 triangles, and 4 times 180 is going to give us 720 degrees. I'll write that bigger down here. So that 720 is the sum of all those angles inside. Now, what is it going to be for one of those angles? So what is this angle itself going to be? Well, that would be that 720 divided by 6, which is 120 degrees. So that's just one of our angles. So this is a really interesting thing that we can do here. We can kind of see a pattern that's starting to develop. This 360, remember, was 2 times 180 degrees to get that 360. So as you're starting to notice patterns here and see what happens, I want you to continue exploring this and try to fill out a table. In this table, I've gone all the way through decagon, so I still give myself 4 more examples. Now you can go all the way through decagon. Some people stop at an octagon. Some people keep going on until they hit a dodecagon. Whatever is best for you, that's what I would encourage you to do until you can find this pattern. And then what the best thing to do here with this discovery is see, can you write a formula or a way that we could calculate what the interior angles of a polygon are going to be every single time? So figure out what is that sum going to be. And once we know that sum, how can I figure out what one angle is going to be? Now, once we have that information and we figured something like that out, it's so useful because then we can keep applying it over and over, regardless of how many sides or angles our polygon has. As long as it's a regular polygon, we know that it's going to have this for one angle. But if it's any type of polygon, regular or not, we can still write a theorem for the sum of the interior angles that'll apply to any 6-sided polygon or any 8-sided polygon or any 12-sided polygon. It just depends on if we can write that formula. So I'd encourage you to try that. When you finish, please check out some of my next videos in which we talk about what some of those equations are and some of those formulas that we can use to then figure out what the sum of the interior angles of a polygon are, what an individual angle might be for a regular polygon. We're also going to talk about the exterior angles. It's going to be awesome. So please walk yourself through this discovery activity in which you figure out what that is. And then once you have that, solidify your answer with what we got.